Hello friends, I welcome you in lecture number 33 on Laplace transform. In this lecture we will discuss this question on finding the inverse Laplace transform of these three functions. And for this problem we are going to use this formula which we are discussing since last two lectures. We know that Laplace transform of t times f of t is given by negative of derivative of Laplace transform of small f, which we have denoted by capital F of s, where capital F of s is Laplace transform of small f of t. And if we take inverse Laplace transform on both sides, then we have L inverse of minus df by ds equal to t times f of t. So we are using this formula for this lecture also, and to use this formula first we have to find out derivative of given function of s with respect to s, and then we can use this formula. So with this formula in mind we can easily find out the inverse Laplace transform of each of these functions. So first function is cot inverse of s by a, and that we denote by f of s, cot inverse of s by a. And we first differentiate this capital F with respect to s. Therefore df by ds equal to derivative of cot inverse, and we are familiar with the formula of derivative of inverse cot function. This is given by negative of 1 over 1 plus x square. Instead of x we have s by a here, so we write this as minus 1 divided by 1 plus square of s by a, that is s square divided by a square, and in the product we have to write derivative of s by a with respect to s. So we are using chain rule. Now I take negative sign on this side, so therefore minus df by ds, this is equal to, this we can rewrite as a square plus s square divided by a square, that a square will go in the numerator, and derivative of s by a is 1 by a with respect to s. Therefore negative of df by ds equal to, here 1a will cancel out and we are left with a divided by s square plus a square. Now we take inverse Laplace transform on both sides. Therefore L inverse of minus df by ds equal to L inverse of a divided by s square plus a square. And we know this formula, L inverse of minus df by ds equal to t times f of t, and inverse Laplace transform of a divided by s square plus a square is sin at, and we are interested in small f of t. Therefore we consider this t on right hand side and we obtain our inverse Laplace transform. F of t is nothing but inverse Laplace transform of capital F of s. So this is very easy method. Whenever our function contains inverse trigonometric functions or logarithmic function, we can find out their inverse Laplace transform easily using this method. So we have obtained that inverse Laplace transform of cot inverse s by a is sin at divided by t. So we have completed this first part. In second part we have tan inverse of 2 divided by s square. So we will apply the same method. First we denote our function by capital F of s. Function is tan inverse of 2 divided by s square. Then we differentiate with respect to s. Therefore df by ds equal to derivative of tan inverse, and we are familiar with the formula for derivative of tan inverse x. It is 1 divided by 1 plus x square. Instead of x we have 2 by s square here, so this we will replace by 1 divided by 2 by s square whole square into derivative of 2 by s square. So 2 is constant, derivative of 1 by s square, that is derivative of s raised to minus 2. Therefore df by ds, now we simplify this. Here we will have square of 2 by s square, that is 4 divided by s raised to 4, and 2 as it is. Here we will have minus 2 times s raised to minus 3. Again we simplify this we can rewrite as s raised to 4 plus 4, and s raised to 4 will be in the numerator. This is going to be minus 4 divided by s cube. Therefore we have s divided by s raised to 4 plus 4. This is df by ds, and with negative sign, so 4 into s divided by s raised to 4 plus 4, and we can consider negative sign on left hand side because we require minus df by ds. So therefore minus df by ds is 4 times s divided by s raised to 4 plus 4. Therefore L inverse of minus df by ds equal to 4 is constant, L inverse of s divided by s raised to 4 plus 4. So now left hand side will be equal to t times f of t by the formula which we just have discussed, and we have to decide inverse Laplace transform of s divided by s raised to 4 plus 4. So we give this number 1, and if you recall we have discussed how to find out inverse Laplace transform of this function in one of the previous lectures. So we have to first adjust the middle term for this polynomial of degree 4, s raised to 4 plus 4. So if I consider this as first term, this as last term, I have to decide middle term. So we use this formula, middle term square equal to 4 into first term into last term. We consider first term as s raised to 4, last term is 4, so we have 16 s raised to 4, that is square of middle term. Therefore middle term is plus or minus 4 divided by s square. So we can adjust this middle term s raised to 4 plus 4. This I can rewrite as we add 4 s square and we subtract 4 s square from this. So this bracket is square of s square plus 2, and this is square of 2s. Now using the formula of a square minus b square, this we can write as s square plus 2 plus 2s times s square plus 2 minus 2s, or we can rewrite this as s square plus 2s plus 2 s square minus 2s plus 2. So we will replace this s raised to 4 plus 4 by product of these two polynomials of degree 2, and these two are irreducible. We cannot factorize these two into linear factors. So we keep these two as it is and we substitute them in this function. Our function is s divided by s raised to 4 plus 4. So now s divided by s raised to 4 plus 4 is s divided by addition of these two, product of these two polynomials, s square plus 2s plus 2, s square minus 2s plus 2. So I have replaced s raised to 4 plus 4 by this product. Now to find out inverse Laplace transform of this function, either we can use method of partial fractions, or we can find out the difference of these two, s square plus 2s plus 2 minus s square minus 2s plus 2. So if we take the difference, we can see s square will cancel out, 2 will also cancel out, and we have 4s, and we already have 4 here, so we can consider this 4 inside this, so that we don't have to adjust that 4 also. So we write L inverse of 4s divided by s raised to 4 plus 4. So here we write 4s. So difference of these two is 4s, therefore we can replace 4s by difference of these two. So in the next step, we will write 4s as difference of these two polynomials of degree 2. Just a minute. So in the next step, I am writing denominator as it is, s square plus 2s plus 2, s square minus 2s plus 2, and 4s is replaced by s square plus 2s plus 2 minus s square minus 2s plus 2. So this is now, this we can rewrite as we divide s square plus 2s plus 2 by this product. So s square plus 2s plus 2 will cancel out, and we have s square minus 2s plus 2. Similarly, we divide s square minus 2s plus 2 by this product, and we are left with 1 divided by s square plus 2s plus 2. Now here we have to set last term. If we consider 2 as 1 plus 1, then here we will have s square minus 2s plus 1 plus 1. So I can rewrite this s square minus 2s plus 2 as square of s minus 1 plus 1, that is 1 square. Similarly, I can rewrite this as square of s plus 1 plus 1, that I write as 1 square. You can check, this is s square minus 2s plus 1 plus 1, that is 2. Similarly, this one. So now our function is converted into those functions for which we are having formula for inverse Laplace transform. So now we take inverse Laplace transform on both sides. Therefore, inverse Laplace transform of 4s divided by s raised to 4 plus 4, this is equal to here we can apply that reverse of first shifting theorem. Because I have s minus 1, I will write e raised to t, and this is similar to 1 over s square plus a square. Instead of s, we have s minus 1, therefore we take e raised to t, and we have 1 over s square plus a square like term, so we multiply by sin t. Similarly, here we have s plus 1, that is s minus minus 1, so we consider e raised to minus t and into sin t. So this is going to be e raised to t minus e raised to minus t into sin t, and if we wish, we can rewrite this as 2 times e raised to t minus e raised to minus t divided by 2 into sin t, and this is nothing but sin hyperbolic t, sin hyperbolic t into sin t. So this is the inverse Laplace transform of 4s divided by s raised to 4 plus 4. So now we put that value here, and we find out product of f of t and t. So we can give this number 2. On the left hand side, we have L inverse of 4s divided by s raised to 4 plus 4. So in the next step, we write that using equation 2 in 1, we have in equation 1, left hand side is t into f of t, right hand side is L inverse of 4s over s raised to 4 plus 4, that is 2 sine hyperbolic t into sine t, and we are interested in f of t, therefore we take this t on right hand side, 2 sine hyperbolic t sine t divided by t, and f of t is inverse Laplace transform of capital F of s, that is 2 sine hyperbolic t times sine t divided by t, and f of s is tan inverse of 2 divided by s square, which is equal to 2 sine hyperbolic t sine t divided by t. So in this way we can obtain inverse Laplace transform of this type of functions. In this case we are using this formula, L inverse of minus df by ds equal to t times f of t, and we are using this adjustment for finding inverse Laplace transform. Okay, so first we write this s raised to 4 plus 4 as a product of two quadratic polynomials, and then we replace this numerator 4s by the difference of these two, and then we apply the first shifting theorem for inverse Laplace transform. Okay, fine. So now we consider third problem. In third problem our function is cot inverse of s plus 1. So as usual, first we have to write derivative of capital F with respect to s. It is minus 1 divided by square of s plus 1, and derivative of s plus 1, which is 1. So therefore we have minus df by ds equal to 1 divided by square of s plus 1 plus 1 square. Okay, I have rewritten this in this way. Now we take inverse Laplace transform on both sides, therefore L inverse of minus df by ds equal to L inverse of 1 divided by square of s plus 1 plus 1 square, and by the formula left hand side is t into f of t, and here we have s plus 1, so we take e raised to minus t, and this is like 1 over s square plus a square with a equal to 1, so we have sin t. Therefore f of t equal to e raised to minus t sin t divided by t. F of t is nothing but inverse Laplace transform of capital F of s, so that we replace by L inverse of capital F of s. Capital F of s is function cot inverse of s plus 1. So finally we have obtained the inverse Laplace transform of cot inverse of s plus 1, and it is e raised to minus t sin t divided by t. So in this lecture also we have used this formula, inverse Laplace transform of negative of df by ds, this is equal to t times f of t, where this f of t is nothing but inverse Laplace transform of capital F of s. So this is all about this session. I hope you like this. Thank you very much.